So now let's take a circuit like this one, attach a sine wave here, put a diode there. Let's say ideal diode. Ideal means you only need a hair over zero for the current to flow in that direction. So once this is conducting current, we'll replace it with the short circuit. And now you have a capacitor here. I'll go like this, plus to minus. So that's a capacitor, has a value of C. Well, what's going to happen to that voltage across the capacitor? What is the voltage here, VC or V out? Well, let's watch this. Let's say the maximum value here is 5 volts. The minimum value is -5, just so you get to see what's happening there. So let me enlarge that. So this is the sine wave. That's this signal up there. And continues. It goes on versus time. So what is VC? Well, once this voltage goes a hair over zero, this diode is going to be a short circuit. So the circuit will look like this initially. This will be a short wire. There's my capacitor. So you can see these two are in parallel, which means they're going to have the same voltage. So right here, this will have the same voltage as the source up to this point. Okay, what happens after that? Well, this capacitor is going to charge. Let's say this is 5 volts here. Now this is 5 volts here. So let's pass that point, the peak value. Once you pass the peak value, that capacitor now still has 5 volts across it. But now this one here is less than 5. It might be 4 or 4.5. What's going to happen to that diode there? It's going to be reverse bias, which means no current is going to flow through it. Well, if no current is going to flow through it, that voltage will stay the same. It will not change. Will stay constant. Right here and constant right there. So once you hit that voltage, the output here, V out, will remain the same, which is 5 volts. If this is 5 volts here. Now let's modify that just a little bit. Instead of just a capacitor here, let's put a capacitor and a resistor and see what will happen. So let's take the same circuit. Ideal diode, here we go. And now let's put a capacitor here and a resistor. And again, there's my source. My input voltage is a sine wave. Again, I'm making the assumption now ideal. We'll fix that later when it's not ideal. So let's zoom in on that and see what's going to happen. This is time. And this is that source. Let me put it as a dotted line here. Like this. It repeats itself. So again, once this voltage is a hair over zero, this will be a short circuit. Doesn't matter which one you write first, which one you write second, they're in parallel. And this is, we'll call it V out. Once this voltage, again, we'll use, let's say, 5 here. Just make us understand it. This is going to 0, 1, 2, 3, 4, all the way to 5, up to here. So while this one is increasing, V out is going to be the same. So this is V out here versus that's V in. The red one is V in. Once you reach that point, this is 5 volts, that's 5 volts. So what happens when this one starts to dip down? This voltage here is right there. It's not a 5. It's like a 4.9. Let's see what will happen. This is now 5 volts. This is 4.9. Well, guess what? This diode now is in reverse bias, which means no current going to go through it. The problem is that voltage across this doesn't remain the same. This actually is charged here to be 5 volts at that time. So this becomes like a source going to force the current to go this way and start to discharge. So this will go this way and start to discharge, which means that voltage will start to drop down and will go like this till it hits that value. So we'll start to decrease, for example, let's say to 2 volts. As long as the value of this source is below 2 volts, nothing is going to happen. This is going to be your circuit. Once the value, actually this one exceeds that 2 volts, I'm just using as an example 2 volts here. So this one now will come in and start to charge again. Then it will drop down. Then we'll charge again. So notice what happened to our V out now. It has a ripple in it. And the question is, can we figure out what that ripple voltage is? What the range of value, by how much is it changing? We call that VR, ripple voltage. Or peak to peak. So the V ripple here I'm talking about is equal to peak voltage. The change is right here from here to there. Well, the way we calculate that ripple voltage, the equation in all these electronic books will say it's the current going through it divided by the frequency times the value of the capacitor. When I say the current, I'm talking about what? I is actually your DC load current, the DC value. F is your frequency. In the US, our frequency is 60 hertz. In Europe, the frequency is 50 hertz. And C is the value of the capacitor, which we call that the capacitance. So that's how we calculate the ripple voltage. If you look in some upper level engineering books, that equation might look a little bit different. It might look something like this. It's the V peak times 1 minus e to the power of t divided by RC. And t is really a lot of times we approximate that. We go approximately VP 1 minus e. We use capital T over RC. And what's capital T is the time difference from here to here. That's capital T, which is almost equal to the period, which is T, or the time from peak to peak. So that's why it's approximately. That's more complicated. That's a little bit easier to use. So most electronic books will use this one, but if you're looking for a true result, that's the equation you want to use. Now, how long it takes that time here? Well, the majority of these, if you're looking at rectifiers, for example, so T is really the time required. That's what T is. the capacitor to discharge. Usually T is approximately around 16.7 millisecond for half wave rectifier, and if it's a full wave rectifier, T is approximately half of that number, which is about 8.35 millisecond for full wave rectifier. Why is the time less for a full wave than half wave? Well, quickly, if you look at a half wave rectifier, I'll do that here, and I'll show you the picture. If this is your VN, again, we said V out is going to look like this, or V ripple is going to look like this. That's the half wave rectifier. Now a full wave rectifier, if this is your VN, I wish I got a blue marker, because what will happen now, these actually will flip, they become positive for V out. So if for V out, this becomes like this. It's a full wave rectifier. So what is the ripple voltage going to look like? It's going to look like this, up to here, start to go down, then back to here, start to go down, back to here, start to go down, back to here. You can see actually that period here, from here to here, that time is much smaller. It's almost half the time it takes to go from here to there. That's half the time. That's why that number is half of that. The other thing you will notice quickly, that peak to peak value is much smaller in full wave rectifier than in half wave rectifier. That's the gap right there. From here to there is much bigger than this one. If we are using this equation for calculation, then for half wave rectifier, for example, in the US, F might be 60 hertz. But when you go to full wave rectifier, even the frequency is 60 hertz, we have to use F equals 2 times 60, which is 120 hertz. Twice that number. Because you can see we have double the number actually waves here versus that one. So let's take some examples and calculate actually what the peak value. I'll do it for half wave and full wave rectifier. So here's my question. Let me draw a circuit for us. And I'll do half wave rectifier first. We have a transformer here, ideal transformer. The ratio is 5 to 1. So this is a half wave rectifier again. I said that early. This is my capacitor. And we'll give it a value for the capacitor of 100 microfarad. We'll put a resistor here of 5K. And the question, can you tell me what V out here? Well, not just V out. Let's ask, you know what? Let's give you a number here. Let's say this is 120 volts peak value at 60 hertz. So here's my question. What is the DC load voltage not the AC, load voltage. That's the RMS value. The DC is the RMS value. And let's get the ripple voltage. V ripple. So from the transformer, we'll call this voltage here V1. I will call this V2. The ratio of V1 to V2 is equal N1 to N2. So V1 to V2 equals 5 to 1, which means V1 equals 5 V2, or V2 equals V1 over 5. This 120 is actually the peak voltage. So V2 peak, not the DC, the peak value, which is, we call that sometimes maximum value. That's equal to 120 divided by 5, which is 24 volts. Peak. The DC value, that's the RMS value from old slides. We said the RMS value is equal to what? It is the peak value times the square root of 2. So for a sine wave, cosine wave is always the square root of 2 times the maximum value to get the DC value. So the DC value for that will be the square root of 2 times 24. Let me get my calculator here. Square root of 2, roughly 1.4, times 24, and I got 33.6. We'll say 37. Now the question is, what is the DC load voltage? We got that. That's your DC load voltage. And the second part of the question is, what is VR? Well, VR is the current I divided by the frequency times C. I know the frequency. Now I know C. What is I? Well, I can use Ohm's law to find I. I know the voltage right here, these two in parallel. I know the voltage here is 37. So I equals Ohm's law, voltage divided by the resistor. What's the voltage? 37. What's the resistor? 5K. So what's 37 divided by 5K? I'm using 33.6, but divided by 5K, it's roughly 6.7 to, if I use 37, so 37 divided by 5 is 7.4. So what is VR equal to? I, which is 7.4 milliamp, divided by frequency, which is 60, and capacitor, which is what? 100 microfarad. Micro is 10 to the negative 6. So let's take that number. So divided by 60, divided by 100 micro. Where is the EE power here? Here we go. EE to the negative 6. And I got roughly, it looks like 1.2 volts peak to peak. So the ripple voltage, that's a half wave rectifier. Where's that picture of it? The gap from here to there, it's 1.2 volts between this end and that end. There's a big changes there. Now again, the other thing here, we made the assumption the diode is ideal diode, which means there is no voltage drop across it. What happens if that diode is not an ideal diode? Second approximation. If the diode is not ideal, then we have to use the voltage across the diode to be, for silicon, 0.7. So going back to this one, that means the DC voltage now, VDC, I'll put it there so you get to see it. So now VDC becomes what? It becomes 37 minus 0.7. Again, if I carry the real number, that'll be 33.3 volts. And the ripple voltage, let's find the current too. We need the current. I equals V over R, which is 33.3 divided by 5K. 33.3 divided by 5,000. It is 6.6 milliamp. So the ripple voltage here will be I over FC, 6.6 milliamp over 60 times 100 microfarad. Divided by 60, divided by 100, e to the negative 6. And the ripple voltage becomes 1.1 volts peak to peak. So now instead of being 1.2, shrunk to 1.1 volts peak to peak. The one thing I will remind you, actually, if you were to build this in the lab or troubleshoot it, when you grab your capacitor, take a look at it. Some capacitors are polarized. What does that mean, polarized? When you look at them, they have a positive and negative end. So when you look at your capacitor in the lab, it looks something like this, a little blob there with two wires coming out of it. Those, one will be charged positively, one will be negative. So if you use one of these capacitors, not all of them, but some capacitors are polarized. If you are using one of these, make sure that you look carefully there. Because that end, the plus end of that capacitor, must be attached to the positive end of that source there. If you reverse that polarity, this capacitor will get hot and may explode. So just keep an eye on that if you decide to build that in the lab and test it, if you're using polarized capacitors. Now, let's take the same filter here that I used. I'm going to use the same filter, meaning what? I'm going to use the same value of the capacitor, the same value of the resistor, this whole circuit, but now take this and attach it to a full wave rectifier. We'll do it for center tap and bridge filter, and we'll calculate what the ripple frequency should be. So let's try center tap full wave rectifier. Same one, 5 to 1, center tap that's attached to ground, and we have we'll assume it's ideal again, just like before. Then we'll change it to non-ideal. And here's my capacitor, 100. We use 100 in the previous one, 100 microfarad, and my 5K resistor. That's also attached to ground here. And let's put a sine wave here, same sine wave we had before. we'll use 120 volts peak value and 60 hertz. And the same exact question, what is the DC load voltage and the ripple voltage, VR? If this is V1 again, and this is V2 from top to bottom, V1 to V2, just like before, is the ratio of N1 to N2, which means what? V2 is going to be 24 volts, just like before. But now we got a problem. Here's what's going to happen. Because this is center tap, that means this voltage here is going to be half of that number, 12, and this voltage here is going to be 12. So if you look at your circuit without this one, for the positive cycle of this, what you're going to see, again, I'm looking at the positive cycle, this is what you're going to see. You're going to see a source here, basically equal to 12 volts, a diode, which is going to be forward bias initially, but I'll put it there, a capacitor of 100 microfarad, and the resistor of 5K. And during the negative cycle, this is going to be negative 12, because the whole thing will be negative, and this one will be on and attached to these two. So if this is ideal, that means there's no voltage drop there. That tells me the voltage here across this VL is equal to 12 volts. Again, that's not a DC value. The DC value is going to be the square root of 2 times 12. And what do we have? There's my calculator there. 12 times the square root of 2. And that's roughly 17 volts, 16.97. So that's the DC load voltage. And when we go into the negative cycle, guess what? The current's going to go this way, and it's still going to be 17 volts. So what's the ripple VR? It's I over F times C. But I is going to be what? The voltage divided by the resistor, which is what? 17 divided by 5K. 17 divided by 5,000. 3.4 milliamp. And the frequency here is twice the frequency, 2 times F, which is 120 hertz. For a full wave rectifier, the frequency is twice the frequency. So what is my VR equal to? It's going to be 3.4 milliamp divided by the frequency, which is 120, times the value of the capacitor, which is 100 micro. Now let's see what that number is. Divided by 120, divided by 100 micro. And it's 0.28 volts peak to peak. Much smaller. So that's why when you look at the full wave rectifier, again, if your input source looks like this, if I don't have the capacitor to filter it, my output voltage will look like this, VL. But because of that capacitor being there, that's going to make it go like this, shrink down, go like this, shrink down, jump there, come down, up there, and repeat the process. That gap from here to this, between the low and the high, it's 0.28 volts, almost a constant value you're getting there. And that's what you want to have if you want to create a power supply. You want that value to remain the same. And again, for all these calculations, I made the assumption the diode is ideal. What happens if that diode is not ideal? That means your voltage, where's my voltage here? VL was 12 volts. So if it's not ideal diode, the VDC it's not going to be 17, it's going to be 17 minus 0.7, which is what? 16.3 volts. I is going to be different. I is going to be V over R. 16.3 divided by 5K. 16.3 divided by 5,000, which is 3.26 milliamp. And V ripple now is going to be 3.26 milliamp divided by the frequency, which is 120, the capacitor 100 micro. I got an error, so let me try it again. 3.26, oh, clear everything. 3.26 e to the negative 3 divided by 120 divided by 100 micro, and I got 0.27 volts peak to peak. Notice not much of a difference really between them. 0.28 volts peak to peak, 0.27 volts peak to peak. I can live with that. Almost done. The only thing left, what will happen if you have a, instead of center tap, what about if it's a bridge rectifier? So let's take a bridge rectifier, attach the same filter to it, and see what will happen. That would be the last thing to do. So, again, I'm using the same numbers. I don't want to change anything. 120 60 hertz. Five to 1. If you don't like to connect this in a diamond configuration, I'm not a fan of diamond configuration, you can actually make the line straight. It doesn't have to look like diamond. And this one is attached to ground. This is where the capacitor is, 100 microfarad, the 5K. And that's again V load. This one I have it backward there. Somehow it fell asleep here. So this should be going that way. Going down, going up there. This one going to the right. And that one should be going in that direction, going that way. So, oh, I'm making a mess here. I don't have white out. That's the direction of this. It's going that direction. Let me see if I have white out here. Nope, no luck. No. Okay. But that's the direction of it. Now, again, if this is V1, V2, I'll jump through it quickly. We did the calculation. V2 is going to be 24 volts. And again, when this is positive current going to come down this way, there's going to be a forward bias, goes down, and there's my filter right there. So your circuit will have really here on this end 24 volts. Up there, if it's ideal diode, that's 0 voltage here, short circuit. This will be reversed, that will shut it off, it will not be on. 100 microfarad, 5K, and there's VL. So you can see the three of them are connected in parallel. That means VL equals 24 volts, and that's an AC value. So the DC value is going to be the square root of 2 times 24, and roughly that's 37. Which means my current I is going to be 37 Ohm's law divided by 5K. 37 divided by 5,000. 7.4 milliamp. And now my VR, ripple voltage there, I over FC. I is 7.4 milliamp. Remember, F here, that's a full wave rectifier, so it's 120, not 60. And C is 100 micro. So let's do the math here. And I'm getting 0.62. Peak to peak. That's your ripple rectifier. I mean, ripple voltage. A little bit bigger. So for a bridge rectifier, the ripple voltage is going to be a little bit bigger than center tap rectifier. Can we recalculate this if it's not ideal? Well, if it's not ideal, what are we going to have actually is VR or VDC here. It's not going to be 37. It's going to be 37 minus 0.7 here, and 0.7 across the other one is going to be 1.4. Which is 35.6. And that will give me I to be 35.6 over 5K which is 7.12 milliamp. And now the ripple voltage is going to be 7.12 milliamp divided by 120 times the value of the capacitor, which is 100 micro. And let's see what that number is. And that's 0.59. No big deal. So you can see the second approximation for all of them, not too far from the first approximation. So if you really want to have a DC value, if you look at your numbers, you want to have a constant value, this will be the ideal solution to get this, but it's not going to happen. Now, if you do half-wave rectifier, the ripple voltage can vary by 2 point, or no, is it? Where's the number? Ripple voltage. Did we calculate that? Yes. By 1.2 volts peak to peak, the gap between the peak and the bottom, top and bottom. That's a big gap there. If we go to a full wave centered like this one, my ripple voltage was the gap from top to bottom. It's only 0.28 volts peak to peak. 0.27 if it's not ideal. And if we do a bridge rectifier, the gap is a little bit bigger than center tap, 0.62 volts peak to peak, and 0.59 if it's not ideal. Good luck.